My name is Aleksandra Ziłkowska, and I would like to tell you about my work on Young-Baxter integrable Lindblad equations. This work, with Fabian Essler, has been published in SciPost Physics. In this video, I will briefly introduce the concepts of integrability and Lindblad dynamics, as well as show how combining them brings us non-trivial results about interacting many-body quantum systems. I will also present some examples of such results. What I mean here by quantum integrability is the property of having an extensive number of local conservation laws. This feature brings a number of simplifications to the calculations. The scattering processes for integrable models conserve the number of particles and can be always factorized into two-body processes. Thanks to these properties, a number of powerful mathematical techniques have been developed. They allow for exact analytic calculations of spectra and eigenstates. In this video, I want to show you that these powerful techniques are also useful outside of the realm of integrability. In my work, I have applied the integrability techniques to the problem of Markovian open quantum systems. Open systems interact with their environment, and this results in the information loss. If this interaction is Markovian, meaning with no memory, we can describe the time evolution of an open quantum system by the Lindblad equation shown at the top of the screen. It contains a familiar Hamiltonian time evolution in the form of a commutator, but also an additional contribution. The L operators, called the jump operators, describe the nature of the interactions between the system and its environment. The dissipative dynamics renders the time evolution non-Hermitian, which further complicates the calculations for interacting models. Some progress has been made by using perturbative and numerical methods. Strikingly though, in a few examples shown on the screen, it was even possible to obtain exact analytic results for interacting open quantum systems. What's more, all those results exploited integrability techniques. In our work, we have attempted a systematic approach to finding a connection between the Lindblad equation and the integrable Hamiltonians. In this way, we have found entire classes of integrable models with open system equivalents. Our approach to the problem was to recast the Lindblad equation into a superoperator form. Under this vectorization map, the density matrix, which describes the state of the system, becomes a state vector in a higher dimensional Hilbert space. The time evolution of the state vector is now governed by the Lindblad superoperator, which acts on this enlarged space. In the superoperator form, the Lindblad equation contains two species of operators, shown at the bottom of the screen with or without an overbar. They correspond to the left and right acting operators in the non-vectorized form of the equation. Now we can look at the terms in the Lindblad superoperator as acting on a ladder, where the two legs correspond to two disjoint subspaces. The terms circled in red contain only one operator species, and hence they act on only one leg of the ladder. The term circled in blue contains both operator species. It links them and acts on the rungs of the ladder. Now we are arriving at a more technical bit, in which I want to show you that the same ladder structure is present in a class of integrable models called the generalized Hubbard models. A Hamiltonian is a conserved charge of an integrable model and can be obtained as a derivative of its R matrix, which is an object related to the scattering matrix. A free fermionic R matrix fulfills both the Young-Baxter and the decorated Young-Baxter equation, as defined at the top of the screen. We can combine these two expressions to form a Young-Baxter equation with a new glued R matrix constructed from the two species of free fermionic R matrices. Due to the structure of this R matrix, its derivative with respect to the spectral parameter contains two terms which involve only one R matrix species and an interaction term between them. This Hamiltonian can be thought of as acting on different parts of a ladder, exactly like a Lindbladian. Thanks to this observation, we have found an equivalence between the generalized Hubbard models and superoperator Lindbladians. As an example, I will show you the simplest case of spin half fermions with Hubbard interaction. For this model, the mapping onto a Lindbladian has been originally realized without the R matrix considerations in the work by Midyedieva, Essler, and Prosen. Consider an open quantum system of spinless fermions, in which the Hamiltonian is the nearest neighbor hopping, and the jump operators are a local dephasing noise. The Hamiltonian part of the Lindbladian maps through vectorization onto a tight binding model. The dissipative part is mapped onto a density-density interaction. This Lindbladian is equivalent to the Hubbard model Hamiltonian with imaginary interaction strength. It turns out that despite this imaginary interaction strength, the Bethe-Ansatz equations for this model have the same structure. The solutions to those equations, called the Bethe roots, characterize the eigenfunctions of the model. In the thermodynamic limit, they are arranged in string-like patterns. The only difference with the usual Hubbard model is that this time the strings are symmetric with respect to the imaginary rather than real axis, as shown in the inset of the figure. Looking at string solutions allows us to obtain information about the spectrum of the imaginary interaction Hubbard, which is plotted in the main figure. The steady state of this dissipative model is an infinite temperature state. The system approaches equilibrium diffusively, which is indicated by a 1 over L squared dependence of the eigenvalues of the highest weight states. Having obtained this information, we need to understand it in the context of an open quantum system. At the level of the integrable model, the Bethe roots determine the wave function, which in turn determines the state vector. Now, the dynamics of the state vector governs the behavior of the correlators in the equivalent open quantum system. The time evolution of a correlator depends explicitly on the Lindbladian action on the state vector. A simple calculation shows that the correlation function in the open system is completely determined by the eigenfunctions of the integrable Hamiltonian. In this way, we can use the integrability techniques to obtain exact analytic results for interacting dissipative systems. I have shown you the simplest example of using the connection between the Lindblad equation and an integrable model. However, we have found entire classes of integrable Hamiltonians with open system equivalents. The first example are GLN-Masarani models, to which belongs the XXZ model. We have also successfully mapped graded Masarani models, GLN magnets, as well as graded magnets. A few low-dimensional examples of the equivalent open quantum systems are presented on the screen. In this video, I have told you how, thanks to the integrability techniques, we are able to obtain exact results for interacting open quantum systems with Lindblad dynamics. In the case of the generalized Hubbard models, I have shown how the equivalence with the Lindbladian is hidden in the underlying R-matrix structure. This work is just one example in an increasing body of research in which well-established integrability techniques are applied to a wider variety of problems. I'm sure we'll see their relevance reaching even further in the coming years.